Welcome everyone. The question that is displayed on the screen, that is the question came in the CBSC 2025, and this is the come in the set 1, section B, question number 17. This question is from the chapter photoelectric current, that is the work function and all of these things is related, Einstein's photoelectric equation. Let us read the question. The work function of cesium is 2.14 electron volt. First question is asked, find the threshold frequency for cesium, and B is find the wavelength of the incident light if the photocurrent is brought to zero by a stopping potential 0.86. Okay, so let us recapitulate what the basic is. Okay, actually photoelectric effect is something which cannot be explained by Leonard and all. Okay, but Einstein basically pioneered this thing. Einstein have told that when the radiation that is falls on a surface and the photoelectrons are coming out, you can consider these radiations have a particular frequency and it is consists of the photons, which is the quanta of the light. Okay, and each and every metallic surface or the metals have some work function. Okay, what is this work function? This work function is basically the energy required by the electron to tearing apart the bond with the others and come out and eject from the surface. Okay, so this is the photoelectron, you can say, which is comes out from the surface. So at first what we can say, if the photon of energy h nu, we can say the beam of photons of energy h nu falls on the surface. Obviously there is two probability. Due to the collision, either the electron which is embedded within the metal can absorb that photon, the full, not half, because it is quanta, you cannot take the half of the photon. If it absorbs the full, then what will happen? After absorbing that, if the energy of the photon, that which is the h nu, if it is greater than that of the work function, what is work function? Just I have said, the energy required for the electron to come out from this metal surface. If the energy of the h nu is greater or equal, if equal, then the photon just comes out from the surface. If greater, then the photon comes out with some energy with it. Okay, so it is designed like this way, that is, if you give h nu amount of energy to a photoelectron, to an electron, it absorbs w naught amount of energy to come out, and the rest of the energy, that electron which becomes the photoelectron now, because it comes out from the surface with the by absorbing the photon, it have that much of amount of energy when it comes out from the surface. Okay, h nu minus w naught. Okay, just like if I say, if the photon is of energy 10 electron volt, okay, if the photon is of energy 10 electron volt and the work function is defined, obviously it is defined for the different surfaces, it is constant for the different surfaces. If it is said it is 8 electron volt, okay, then 10 electron volt minus 8 electron volt, 2 electron volt, that 2 electron volt now becomes the energy of the electron with which it comes out from the metallic surface. Okay, so obviously from here it can be understood that as the work function is there, along with that, if h nu is greater than equal w naught, then the photoelectron comes out. So the incident radiation must have some threshold frequency, which is defined as mu naught. If the photon have that amount of energy which is equal to that of the w naught, that is the work function, then what will happen? After absorbing the photon, the photoelectron comes out. So nu naught is the frequency of the incident radiation, what it should be, otherwise the photoelectron not comes out, and that is a threshold frequency. So the threshold frequency can be written as W naught divided by H. Okay. So let us return back to the first question. What is said? Find the threshold frequency for cesium. I repeatedly said, and again I am saying, each and every metal have a particular value of the work function. It is the characteristics property of the metal. Here it is said for the cesium. So cesium have the work function 2.14 electron volt. So we can say W naught. We can say W naught. That W naught is 2.14 electron volt. If I want to convert this thing in the joule, then what will happen? It will be 2.14 multiplied by 1.6 multiplied by 10 to the power minus 19 joule. Okay. Now what is relations between the threshold frequency and the work function? How to find it out the threshold frequency? If you know the work function, this is the formula. That is the nu naught equal to W naught divided by H. Okay. So it is 2.14 multiplied by 1.6 into 10 to the power minus 19 divided by, obviously, the value of the H, which is a Planck's constant. It is 6.6 multiplied by 10 to the power minus 34. Okay. So 6.6 or 6 to 6, you can say 6 to 6 into 10 to the power minus 34. Okay. So 1.6, 2.14, 6.6 to 6. So I can write it down simply as 214 multiplied by 16 divided by 6 to 6 multiplied by 10 to the power minus 19 plus of 34. I hope you understood that, the decimal points cancellations. So let us cut it down. If you cut it down, it will be 313 and it will be 8. Okay, 313 and it will be 8. Now we have to do multiplication. Then 8 4 ja 32, 8 1 ja 3, so 11, 8 2 ja 16, so 17, divided by 3 1 3 multiplied by 10 to the power 19 minus 34, so 5. Okay, and 1 2, so 15. Please check it out. 10 to the power 15 it is. So 1712. So approximately we can say it is of the order of, this is the order for 5 something. So 5 into 10 to the power 15, you can say that frequency A incident photon should be. If the frequency is less than that of the 5 into 10 to the power 15 Hertz, then you will not see the photoelectric emission. Next question is, find the wavelength of the incident light if the photocurrent is brought to 0 by the stopping potential 0.86 volt. And this question is asked from the Leonard experiment. Okay, what is Leonard experiment? Leonard has done one experiment. Let us draw the apertures. It is the thing. This is a vacuum tube which is taken at that time, and obviously, but there is a window. Okay, through the window the radiations comes. Okay, radiations comes, and here the radiation falls on this. Radiation falls on this. Then what will happen? The photoelectrons are coming out. Photoelectrons are coming out, and these photoelectrons are basically collected by it. So you can say this is the emitter here, which is emitting the photoelectron. Okay, and this is the collector here, which is collecting the photoelectron. Okay, obviously if you make it positive and if you make it negative. Okay, but I have just said, if you made the photon of energy h nu and w naught is the work function, then the photoelectron which comes out have some energy which is half of m v max square. So the photoelectron which comes out from here, it have some energy half of v max square. With that energy, it just proceeds towards the collector plate. Now think, if you made this thing not positive but just reverse this thing, then what will happen? If you made the collector negative and the emitter positive, the photoelectrons comes out and it is just propagating towards the collector, which is not the collector now, but it is a negative potential. So what will happen? It is getting repelled by the C. It is getting repelled by the C. Clear? So since the C is kept at the negative potential, so it is repelled by the C, but still it is just tearing apart this electric field and try to reach the C, because it have that energy with which it comes out from the metallic surface. Okay, so what we will do, if you increase this negative potential compared to that positive, then what will happen? You will see the photoelectric current. If I draw here, you can see it. If I draw here, this is the current and this is the voltage. Voltage means voltage applied on between the E and C. Firstly, when you make the V0, it is here. But if you increase the V, then obviously the photoelectric current is increasing like this way. But if you make the C negative, if you start repelling the current, the photoelectrons which comes out from E, then it will start decreasing, and at a certain value of the V, the current becomes 0. And that particular V0 is called the stopping potential. So just think, electron is propagating towards it. So E V0 is the energy, and that is equal to 1 by 2 m v max square, and that equation have a significance. When you made the potential between the collector and the emitter, obviously the negative one is equal to V0, then the electron which is having the maximum energy which is comes out from the emitter and try to reach the collector, okay, cannot reach. Okay, just cannot reach, because due to this negative value of the potential difference, due to the opposing electron field, it just stops. Okay, so this in this expression h nu, okay, minus w naught sometimes can be placed as h nu naught, and half of v max square can be placed as a ev naught. Okay, so if you know this, that is nu equal to c by lambda, then you can say it is c divided by lambda minus of h c divided by lambda naught equal to E into V naught. Okay, E into V naught. If you take Hc common from here, then you can say this Hc divided by E equal to 1 by lambda minus of 1 by lambda naught equal to V naught, that you can say. Now let us go back to the question, what they have said. Find the wavelength of the incident light if the photocurrent is brought to 0. Obviously you understand how the photocurrent brought to 0 by making the collector negative by a stopping potential 0.86 volt. Okay, so now we know this equation. What is this equation? The equation is h nu minus of h nu naught is equal to E V naught. Okay, so h nu, the nu or the frequency, you need to find it out. Okay, if you know the frequency, you can find it out what is wavelength. So it is h nu we need to find out. Nu naught we already calculated, 5 into 10 to the power 15 multiplied by E. What is E? 1.6 into 10 to the power minus 19. What is the value of V naught? It is 0.86. It is 0.86. Okay. Then what will happen? If you want to find it out what is nu, then if I write it down, then obviously it will be like that. That is E divided by H multiplied by 0.86 plus of 5 multiplied by 10 to the power 15. Okay. So what is E? E is 1.6 into 10 to the power minus 19. What is the value of the H? It is 6.626. So let us make it 6.6 multiplied by 10 to the power minus 34. 10 to the power minus 34 multiplied by 0.86 plus of 5 into 10 to the power 15. 10 to the power 15. So 1.6 into 10 to the power 9. So 16 1 just 16, 16 2 32, 16 3 just 48, and 16 4 just 64. So we can say 16 by 6.6 can be written as 1.4 multiplied by 10 to the power minus 19 plus of 34 multiplied by 0.86 plus 5 into 10 to the power 15. So this will become 0.4, that is we can say this is 0.1, or approximately it is 0.165 into 10 to the power 15 plus 5 into 10 to the power 15. Okay, so this will become 5.165 into 10 to the power 15, and this is the frequency. Okay, this is the frequency. But if you want to know what is the wavelength, then we know that nu equal to c by lambda. Nu equal to c divided by lambda. So if you want to know what is lambda, lambda equal to c divided by nu. What is c? 3 into 10 to the power 8 divided by what is the frequency? 5.165 multiplied by 10 to the power 15. So if I calculate the order, then we can say it is 3 1 2 3 divided by 5 1 6 5 multiplied by 10 to the power minus 7 meter. So if we do it, obviously 3 by 5, if we think it is 3 by 5, then 3 by 5, if I approximate as a 3 by 5, then it is 0.6. It is approximately 0.6 into 10 to the power minus 7 meter. So this can be written as 6000 into 10 to the power minus 6000 into 10 to the power minus 10 to the power minus 10, not 10 to the power minus 11 meter, or you can say this is 600 angstrom, because obviously you know this and thing, and obviously or 60 nanometer. So this is the answer of the part B. Part A answer already we get 5 into 10 to the power 15 hertz. So I think you understood these things, and theoretical background, the basics are already discussed. So I think every doubt is clarified. If any doubt arises about this question, obviously write it down in the comment. Thank you all of you.